this into trig functions of any angle, which is 13.3, which will build into 13.4, which is using invert stuff. What we're able to do here, guys, is that we're going to be able to take the trig values of any point on a two-dimensional grid and find the 6 trig functions. Now, depending upon the style problem that we have, we may or may not have an angle that lies within our unit circle. We may or may not just have an ordered pair that's out in space that we can still find all the trig functions of. It's just a matter of how we're going to set them up. Each one of these kind of sets up the same. And it's just a matter of getting accustomed to how it looks in relation to two-dimensional space. Okay. So when you're dealing with trig functions, we already know that we have the 4 quadrants. Okay? We know that it's positive, positive, negative, positive, negative, negative, and positive, negative. We also know our 6 trig functions. Cosine, sine, tangent, and the inverse functions. What's the inverse of cosine? Secant. Remember? Secant, cosecant, and cotangent. Okay. Those are the trig functions. So when you use that inverse button on your calculator, what you're finding is what angle has versus flipping the reciprocals. Okay. Now, cosine is adjacent over hypotenuse, therefore secant would be hypotenuse over adjacent. They're just reciprocal, they're the reciprocal properties. Okay? And I know we've talked about this in the past. Now, we've also known that if cosine is positive here, what else would be positive there? Secant. Since they're inverses of one another, they're both positive in the same spot, which means they're both, oops, that didn't work as well as I hoped. They're both negative here. They're both negative here, and they're both positive here. So the trig functions and their inverses, the reciprocal ones, they have the same signs, SIGNs, as we go through. All right, it's pretty easy to work with. But sometimes you're going to be working with this. And I'm going to rewrite this to make this look a little bit cleaner. If you take any point and put it into a quadrant, I don't know what it is, just picking some random ordered pair. That ordered pair, we're always going to draw a terminal side to the origin coming up like this. Okay. If I place that theta at the origin, I can then drop some vertical component, and I have some horizontal component to create a right angle. So it creates a right triangle. Since we're dealing with this in terms of a circle, that terminal side of theta we're going to call r. Is that all right? This distance is x, good. And this is y. Now, you can write any of the trig functions in terms of x, y, and r. Ooh. What's the cosine of theta? X over r. What's the sine? What's the tangent? Then what are the reciprocals? You just flip them. You just flip them all. The reciprocal properties are all just flipped. What's that?
Figuring out how to do the theta.
Oh, theta. Yeah, it's kind of like
theta.
it's kind of like an oblong O.
Yeah, that's what I do. I do an O and I just totally do it.
Mm-hmm. If you use it in like Word or something like that, it looks like a 0 with just that, like that. Like a what? Is that what Pepsi looks like? I never noticed. I don't drink Pepsi, so that's probably why I didn't know. So what's secant gonna be? Cosecant and cotangent. So now what you can do is I can give you guys any ordered pair, and you can create all the trig functions from that one ordered pair. Example. If I take the ordered pair -3 and 4, and I want you to write out all the 6 trig functions for that theta value.
Okay, hold on, give me a second.
What quadrant are you going to go to? You go to your second quadrant. There's your point. Terminal side to there. Theta comes up. What's your opposite? 4. What's your adjacent? -3. What's your radius? Oh, very good. Yes.
Forgot about that.
Think of the ordered pair. It's the export. Huh? You went to the left. It's placed in space. This is the reason why cosine is negative in the second quadrant, because your adjacent value is negative. Okay. That's why your cosine value is going to be negative. That's also why your sine value is positive, because you have a vertical component. That's why all those little things I've been kind of hinting at as we've been going along, why these things happen, is because of this. So now you can list through your trig functions. That's all it is, man. That's all it is. So looking at this, you could probably take a fairly decent educated guess as to where tangent and cotangent are both positive or negative. If tangent and cotangent are going to be positive or negative, that means both of the x and y values have to have the same sign, SIGN. Where does cosine and sine have the same positive or negative? Where are they the same? Where do cosine and sine have the same sign, SIGN? Which one? First and third. So where do you think tangent and cotangent are positive? First and third. Because what's a negative divided by a negative? Positive. What's a positive divided by a positive? Positive. That's why tangent, let me show you here. So what you're going to get here is, it's positive, positive. So cosine, sine, and tangent is also positive. Negative is positive for cosine, sine, which means tangent is negative. Negative, negative for cosine, and sine, which means tangent is positive. And then positive, negative for cosine and sine, which means tangent is negative. Because the way that the fractions work, opposite over adjacent, if your opposite and adjacent have the same sign, SIGN, you're dividing it, 2 negatives make a positive. And that's how that works. All those work also for reciprocals. Okay. Cotangent's positive, same 2 quadrants, just like cosecant and secant are as well. Okay. Not too scary? It's a lot of little right triangles, a lot of little right triangles. Oh, we just did that. The other side. Let's try one more with the 6 trig values. There's your point in space. Well, let's figure it out. So you obviously have to figure out your quadrant, place it, and then do a quick little Pythagorean theorem, or, I don't know, sometimes you find triples, sometimes you won't. Remember the shortcut here? Notice how everything's going, the triangles are always going back up to the x-axis. Okay. So, what's your opposite?
15.
Negative 15.
Negative.
What's your adjacent?
Negative
Negative 12. What's your hypotenuse? Oh, what is this decimal stuff? I don't know. How do you simplify radical? It's not 3, 4, 5. Let's see, where is that?
Yeah.
12, 15.
That would be 4, and then 5, 15, and 3, 5. So 5, 4, 9 would be 3.
Oh,
So it would be 9.
wouldn't you want it has to go with the hypotenuse. You go to your y equals. Oops. Some fun graphs there. It was what 15 and 12, so 144 and 225 is
369.
looks like 341 to me.
Oh my god.
Remember that? Divided by x squared. Yeah. Divided by x squared, you're looking for the last integer value you get in the y column before it goes all decimals. So the only tricky thing here is that you have to do some rationalizing. Okay. Vaguely remember that?
Maybe a little bit.
All right. So what's that? X squared. So if I'm going to do cosine x over r, so it's going to be negative 12 over 3 root 41, which means I have to rationalize and simplify my fraction. So right off the bat, I know that this is going to be negative 4 over root 41. Does everybody agree that I have to rationalize to make this correct?
Yes.
Okay. Before I do that, what's secant?
441.
What I'm doing here is I'm going to do the secant value first before I rationalize, so I don't have to re-rationalize later. Because if I just flip it right away, I've got my fraction for that. There's my secant. But when I rationalize the other one, I'm going to get negative 4 root 41 over 41. Never multiply the top and bottom by the radical. It's just a nice little trick. You don't have to do it that way. I just know that whenever I see a standard sine, cosine, or tangent, the radical in the denominator, when I go to have to buy the inverse of it, the reciprocal property, I just flip it and write it down right away before I go back to rationalizing. That's all. The rest of them are pretty easy to work with. I just wanted to show you guys that little bit of a trick. I kind of wanted to spend more time on the really fun ones. quadrantals. There are 4 quadrantals. It's where the unit circle crosses both the x and the y axis as you're going around. The reason we call it the unit circle because we're giving it 1 unit of measure as it's going around. Which means we can find, yeah, you left it on there. Which means you can find the ordered pairs for each one of those. For example, what's the ordered pair there? 1, 0. What's the next one? 0, 1. Next. And, okay. What's your radius when you're on the quadrantal? 1, very good. So here's what happens. Let's pick pi over 2. Let's run the 6 trig functions at pi over 2. Okay. Sine, or cosine, sine, tangent, and reciprocals. Let's move this over a little bit. What's x over r for cosine? So what's the cosine at pi over 2? Zero. Cosine at pi over 2, it's x over r. What's x at pi over 2? 0. What's r? 1. What's 0 divided by 1? 0. What's the y coordinate? Yes, ma'am. No, go ahead.
No.
Please. Remember, you're the voice of reason in here. And that's not a bad thing. It's good.
No, I just.
Okay. What's the y value at pi over 2? What's the radius? 1. What's 1 divided by 1? Again, what's the y value? 1. What's the x value? What's 1 divided by 0? Cannot be done, so it is undefined. Think about the reciprocals. If I flip my reciprocal at cosine, I get 1 over 0. What's the reciprocal of 0? Undefined. So that means secant zero and undefined are inverses of one another. You guys probably remember that from slopes. Sure do. They're reciprocals of each other. Remember, that's how you knew they were perpendicular. They formed right angles. They had opposite reciprocals to one another. Horizontal lines have a slope of 0. Vertical lines have a slope of undefined. That's why they're perpendicular. That's where this comes from. What's the reciprocal of 1? 1. That's why cosecant the reciprocal of 1 is 1. What's the reciprocal of undefined then? 0. 0. Very good. So cotangent is x over y. Quadrantals are extremely important for graphing. Okay? They're going to be really important for us to graph as we start to graph these sine curves and cosine curves as well as tangents. Because if you think about what sine does as it goes through one full cycle, one period, one time around, sine starts at 0, it goes up to 1, goes back to 0, goes to -1, and then it comes back to 0. So your sine curve does that as it goes graph. So what's that? Cosine, where does cosine start at when you're at 0? Starts at 1, it goes to 0, goes to -1, goes to 0, and goes back to 1. Yeah,
Where are you getting these?
quadrantal. Starts at 0, goes to 1.
You just said it's already.
I'm sorry, I did sine first. Sorry. I start at 0 with sine, I go to 1, I go back to 0, I go to -1, and I come back to 0.
I still don't see it.
Sine value. Sine starts at 0,
Okay.
goes to 1,
Oh,
goes to 0, goes to -1, and back to 0. That's what I was getting at.
Alright.
Here's the fun one. Where does tangent start?
You know.
Start at 0. Think of tangent at 0. Tangent at 0 would be 0 over 1. What's 0 over 1? 0. So tangent, give me the orange, would you? Or no, I need a darker color. Is there black over there?
Blue. And
Tangent starts at 0. Does it ever get to 1?
yeah.
Think about your unit circle real quick. Look at it.
Maybe.
Is there an ordered pair that has the same x, y value?
Yeah.
Think of it. Where? At 45, doesn't it? So at pi over 2. So somewhere in here, it's going to reach 1. And then what happens is it gets closer to 90 degrees. What's the tangent at pi over 2 at 90 degrees? Remember, we just did that. It's undefined. So at this value here, it's never going to be 8. So tangent gets closer and closer to that. And then if you go the other direction, if I just start at 0 and work backwards, it's going to hit 1 again somewhere in here. And there's going to be another asymptote here. So sine, cosine, and tangent curves are all going to be based off of quadrantal ordered pairs. This is still a few weeks away, but I just want to show you the importance of understanding why do we look at quadrantals? Why are quadrantals important for us to be able to utilize later on? You're going to live and die by these things. That was awkward. No, seriously, I mean, as you start to recognize as it's going through its period, as it's going through a full cycle, that's what these values do. Okay? That's what these things are going to do. And then eventually we'll shift them and move them, and then we're going to find the inverses of it, and you'll have drops this way and other asymptotes, and it's fun. H's and K's, yep, good times. Reference angle again. I know I've been harping about reference angles a lot. What was that reference angle, you remember? Yeah, you always want to drop it to x. How far are you from the x-axis? Okay. Your reference angle is always going to be measured as a positive value, distance off the x-axis. Distance and I'll say distance, and I'll put absolute value on it because distance is always positive, so you remember that. Right? Whether it's degrees or radian, it's the same basic idea. If you are in the second quadrant and you're above it, you have to figure out how much more does it take to get here. You know, a little subtraction. If you were below it, how much did I go past it by? Things like that. It's always off the x-axis. So it's above here, it's below there, it's below here, and first quadrant angles are First quadrant angles are their own reference angles. Because in the first quadrant, you are rising from the x-axis as you're coming up. And then the terminal side switches over, and that's your new distance from this side to the second quadrant. Versus over here. What's that? 90 degrees. 90 degrees is a quadrantal. It's on the axis, we don't mess with that. It's its own specific stuff. Okay, because we know that at 90 degrees, it's 0, 1. Everything else is dependent upon its reference angle. That's why quadrantals are a little fancier. Plus you can do this. You guys didn't look like you liked that very much. No.
I mean, it looks
Well, I
cool,
didn't really
but
understand it.
We're taking the two-dimensional and stretching it differently, that's all. We're taking one set of ordered pairs and we're cycling them around. Yes, ma'am?
You go back up one slide.
Yeah.
Okay, how do you know the article?
Unit. That's why we call it a unit circle. So when you have the unit circle, we just give, that's why we say it's 1 unit. It would, all this stuff would still work if it was, 2. And then if this value, if I set this at 2, that means R is 2. These are the old ways of doing it. I don't like to do those anymore. So here's what I want to look at. I want to take and put this out of order. Nope. Thought I had saved it the right way. There it goes. I want to find, I'm going to use a reference angle to find that without using a calculator.
be a lot easier.
Okay.
So we need to use reference angles. And I know we've been drawing them and figuring out where they land in the quadrant, or in the coordinate plane. 11 pi over 4. What? 4 goes into 11 how many times? 2 and how many are left over? 2 and 3/4 pi. So when I start this, there's 2 pi. And then where do I go?
3/4.
3/4, which is the second quadrant. If this is 3/4 of the way, what's my reference angle coming up? A 4. So it would be pi over 4.
So the cosecant.
We're not there yet. Which of the two triangles is pi over 4 in? Is it a 45, 45, 90? 30, 60, 90 has pi over 4. 45s. So what we do is, we know we're looking at we're working with a 45, 45, 90 triangle. I know my side lengths are 1, 1, and √2. And I'm looking for the cosecant. Cosecant is the inverse of which
You
function?
know the size of
Sorry.
Sine. So if the sine would be opposite over hypotenuse, cosecant would be good. So I know that cosecant is going to be opposite, hypotenuse over opposite. So in this case here, it's going to be √2 over 1. With me so far?
it. Yep. Pat, how do we know if the side lengths are 1?
It's special right triangles.
Well, yeah, but couldn't they be like a big number?
Yeah, but they scale back to being, if they were both 8, you'd be 8, 8, 8 √2. You have that scale factor. You take out that scale
okay,
factor.
yeah.
That's why we used to write it as x, x, and x √2. You're trying to find that scale factor of x, but it's just really basically just 1. It always simplifies back to 1.
Got it.
So cosecant, the inverse of sine, so it's hypotenuse over opposite. 45, 45, 90, √2 over 1. Last question, is it positive or negative in the second quadrant? Is sine positive or negative?
Sounds
Sine is positive, so is cosecant. Positive or negative? Positive. So my answer is √2. There's my answer. The cosecant of 11 pi over 4 is root 2.
It's not too bad.
It's a matter of spinning to a reference angle and figuring out which quadrant you lie in. That way you know what sign SIG in, whether it's positive or negative. There's only 2 triangles you got to worry about, guys. 30/60s and 45s. Once you spin it to go through, you'll know where it's placed. What do you got?
Okay, so if it's pi over, if it was like pi over 6, it would be 30 degrees,
Correct.
and then it would be 360.
Yep. And then you'd be using the 30-degree angle as,
It would be the equal way. Closer to that side.
yes, because that's how we place it. All right? And you'll see that it doesn't matter how you draw your triangle, because you're still using the same opposite hypotenuses and all that stuff. It's just a matter of the sign SIG in as you place it within the quadrants. Let's do another one. I'll go to a degree. We're going to mix it with degrees and radians today. Tangent, negative 210. Negative angles go what direction? Which one? Down. They go down and around. Okay. So 210. Where's that going to wind up? Very good. It's going to wind up second quadrant because we come up 180. Then how far up do we go? 30 degrees. So what's my reference angle? 30 degrees. I have a 30-degree reference angle in the second quadrant. So I know I have a 30, 60, 90 triangle. And I'm working with the 30. The tangent of 30 is opposite over adjacent. So the tangent here is 1 over root 3, which is, very good, root 3 over 3. Second quadrant is tangent positive or negative? Negative. So your answer is negative root 3 over 3. You gotta spin it, point it. That's the whole point we taught you guys, those special triangles. Everybody got it.
Wait, so how do you know if it's negative or positive again?
Remember tangent, you've got x and y, Tangent is y over x. So tangent would be positive over negative, so it's negative. Yes, sir?
What if it doesn't land like on 30 or 45?
Then you have to use a calculator.
Okay.
That's all it is. Seriously, that's all it is. You're using, I'm gonna give you guys stuff that's gonna land in the specials because that's the whole point. I want you guys to land and learn in the specials. That's how we do it.
Sure.
Let's do this. Cosine, negative 4 pi over 3. Do I keep giving you guys first or second quadrant problems?
Yeah.
Oops.
It looks like.
Oh. Spin it. Got to go down and up. What's my reference angle? Remember, it's always a positive difference, so it's pi over 3. Pi over 3 is which of the special of the right triangles?
60.
It's the 60. Excellent. So it's the 60-degree angle. Cosine of 60 degrees is how much? 1/2. Is cosine positive or negative in the second quadrant? Go to the next problem. You don't trust me? I'm hoping it's not as frightening as it sounds.
So it's not.
Just looks right.
It does. It looks like it, but if you think about it, the whole idea of this entire chapter, I've been talking to you guys about this whole reference angle idea. How far are you bounced off an axis? How can you relate it in terms of the 30, 60, 90s? Getting that back in your mind as you've been just going through these things, you're kind of getting it, you get in the groove. Go ahead, I was trying to, make sure you were successful as we got further along. I was proactive. 240. 240 drops you to which quadrant? 30 degrees, good. So 240 drops you to the third quadrant. Here's 180. 240 is how far off the x-axis? 60. What's your reference angle? 60. 6-degree reference angle means I have a 30, 60, 90 triangle. Root 3, 1, 2. Tangent of 60 is root 3 over 1. So it's going to be root 3. And is tangent positive or negative there? It's positive. Go to the next problem.
Not too bad.
Spin the reference angle. Figure out which of the two triangles you're working with and go for it. That's how these things work. Okay? That's how these things work. Try these last two. I'll give you some problems. Secant 11 pi over 6. Which quadrant do I drop to? Go to the fourth quadrant. How far am I off from the x-axis? Pi over 6. So I have a pi over 6 reference angle. 30. It's a 30-degree angle. Remember, it's smaller. Secant is the inverse of which one? Cosine. So cosine would be root 3 over 2. So secant would be the reciprocal of that. 2 over root 3. Which is excellent. Is cosine positive or negative in that fourth quadrant? It's positive. Cosine is the x value. Cosine is your x value, so you're positive again. You buying it? All right. Last but not least, tangent 5 pi over 6. Well, you can probably tell you're going to have a reference angle of something. Pi over 6, very good. Second quadrant, pi over 6 relates to which triangle? 30. Tangent of 30 degrees. One over root 3. Root 3 over 3, and tangent positive or negative in the second quadrant. I love trig. That's
Don't look at see me.
I enjoy your excitement.
all right. So let's see. This is 13.3. A lot of spinorama jamma there. A lot of spinorama jamma. Yes, ma'am.
Not saying I didn't trust you. When I typed into the calculator, all the ones that were radicals, I ended
If they give you, because it's giving you decimals, those calculators don't simplify radicals to give you root 3 over 3. And it gives you the decimal equivalent of root 3 over 3.
Yeah. I know, so like I did it.
Are you in radians or degrees?
How many students?
Okay. So that's the other thing. If you take the tangent of, which one was it there? 5 pi over 6, and you type it, if you put it in radians like that, you will get the decimal equivalent of negative root 3 over 3. So you multiply by 3 squared, and you'll see it's like, oh, it's zero. So it does work, but calculators just do decimals. So demanding. The idea